All right, good afternoon, everybody. Good afternoon, everybody. Let's get started. Okay, so welcome to 604. Today we're going to switch gears and talk about CMOS. CMOS is the technology that's used to build chips today. And essentially, so far, we have seen how to design combinational circuits. We have seen how to express those combinational circuits in a hardware description language. We have seen a little bit about the pitfalls of using a hardware description language and the fact that you need to always remember that you're writing hardware. But remember when we said, in the end this thing gets synthesized into a bunch of gates and wires, we sort of didn't specify what these gates actually are. And so this is what we're going to do in this lecture. We're going to go one level below and see how these gates actually are implemented. So let's just start by taking a deep dive into what's inside a computer chip. Right? So you can go to any electronics store today and buy something like this. This is a packaged chip. Right? This is one from Intel. And this in particular is a chip that implements a CPU, the processor that you have in your desktops, your laptops, server, computers, and so on. But this has a bunch of, this is mostly packaging. If you actually pry this open, what you'll see is that there's this tiny die, this tiny slab of silicon. This is what we call a silicon die. And you might have seen some pictures like this. If you just look at it, it will be some sort of reflective metal surface. And this is very small. This is about 1 to 2 centimeters on each side. So 100 to 400 square millimeters. We measure the size of this thing in square millimeters. Now, there are a lot of structures here. And in fact, if you take a look at these chips, if you open up the packaging and just look at the slab of silicon, you can see some structures here. Like there are some repeated structures, and there's some other structures that show up in a different color here. And in fact, it's once you understand what these are, you can start looking into what the different components are and how much area they take. So, for example, these are all memories. These are the 4 cores in the chip. There's a GPU over here. And so you can start reverse engineering what did Intel put in here. But I want to just go even deeper and say that we cut this vertically. This thing has a certain amount of area, and it's about 100 or a few hundred microns tall. Let's take a vertical cut through that. And what you'll see is that there's 6 to 15 metal layers. These are essentially wires. In the bottom layers we have small wires, and as we go to upper layers, the wires get larger and they're used for things like power or far away signals that need to travel through a fair chunk of the chip. And there, right at the very bottom, there are these tiny, tiny structures that are not wires. They're transistors. They're in particular FETs, or field effect transistors. Now, this particular transistor is 32 nanometers wide. It's tiny. That's why you can put billions of them on just a few hundred square millimeters. Right? And these are the devices that are used to implement gates. We just use transistors and wires. So what we're going to do in this lecture is, in the first half, we'll look at how these transistors work from the perspective of, the minimum amount of knowledge we need to build gates out of them. And then, in the second part of the lecture, we'll derive a model that's a little bit more detailed, that can tell us something about the delay of these gates and the area that they're consuming, and a little bit also about the power. Now, the second half is going to be useful when you're synthesizing chips or synthesizing circuits, and essentially you want to figure out why is the delay the way it is. So it's good to understand why, what causes the delay to grow. But that second part of the lecture is not going to be on the quiz. This first one, the how do you build gates out of transistors is. And so I'm going to spend more time going in detail over the first part, the how do you build gates out of transistors, and then we'll cover however much we get to on the second part. Okay, so there are many kinds of transistors. The transistors that are used to build digital logic today are called field effect transistors, or FETs. And the one thing you need to remember about FETs is that they're just voltage-controlled switches. They are 3-terminal devices. There are 2 terminals. And then the voltage of the third terminal is going to control whether there's a connection between the other 2 terminals or not. So there are 2 kinds of FETs, and we're going to exploit these 2 types of FETs. We call them N-FET and P-FET. Let's look at the N-FET transistor first. This is the circuit diagram for it. And so as I mentioned, there are 3 terminals here. There are what we call the source, the drain, and the gate. And the way this N-FET transistor works is a high voltage at the gate is going to create a conducting path between drain and source. And so when you put a high voltage here, let's say at digital 1, you will connect these 2 terminals electrically. If there's a low voltage here, these 2 terminals will be disconnected. And we can use these to build gates. So PFETs are very similar. They are actually just the opposite. First of all, their circuit diagram has a bubble here. There's no bubble in the MFET. There's a bubble in the gate terminal of the PFET. And the way a PFET works is that a low voltage at the gate creates a conducting path between source and drain. Now, there's one thing that we need to discuss before we start building gates, which is that if you look at the symbol, there's no actual physical difference, or there's no actual difference in the circuit diagram between the drain terminal and the source terminal. And also, it's kind of weird that I've labeled the drain up here for the MFET and the source down here. But for the PFET, I've chosen the source terminal to be up here and the drain to be down here. So what happens is, the reason there's no difference in the circuit diagram between the drain and the source is that how we name these 2 terminals, drain and source, is just a convention. Okay? These terminals are physically identical. This device is symmetric. If we go back to this picture over here, this is the gate, and we'll see this in a little bit more detail later. This is the source and this is the drain, but really there's no difference between both. I could call the drain the source and the source the drain. So how do I choose the names of source and drain? Well, source and drain are both what we call the diffusion terminals, and the way we choose to name them is just by the voltage they will have in the circuit. So the source and the drain, among these 2 terminals, there will be one that has higher voltages than the other. And on an MFET, we choose the source to be the diffusion terminal that's at the lower voltage. And on a PFET, we do just the opposite. The source is the diffusion terminal that's at a higher voltage. So that's why I have drawn them this way, with the drain at higher voltage for the MFET, and the source at a lower voltage. And then here the source is the terminal at the higher voltage, and the drain is at the lower voltage. So that's why I label this terminal S and this terminal S. If just thinking about why I'm adopting this convention, what we'll do is we'll draw high voltages up top, right? And then we'll just draw the ground in the bottom, and that way you can always label the source and drain following this convention. Now, this might seem confusing, right? Why do you have this weird convention for labeling things according to voltages? Why do we care, right? If the terminals are physically the same? Well, so the reason for this convention is that it makes it much, much simpler to define the behavior of what each of these transistors does. And let's see this in a bit more detail. So let's start with what we call the switching model. This is like a zeroth order model for these transistors. Transistors are very complicated devices. In the end, to fully understand them, you have to go and take a course in solid state physics. We're not going to do that here. We're going to abstract them. If some engineers working on actually making transistors saw these lights, they probably would cry. So that said, we're just going to use the simplest model that lets us work with them. So the first model we're going to see is what we call the switching model, right? Which is just treating transistors as voltage-controlled switches. So transistors have a threshold voltage, which we denote VTH, and then we say that, what happens is an MFET turns on if the voltage between the gate and the source, which we call VGS, exceeds the threshold voltage. Otherwise, the transistor is off. That means there's no conducting path between source and drain, right? So we draw it this way. There's the source over here, the gate over here. VGS is the voltage between these two terminals, and if VGS is less than the threshold voltage, VTH, then the transistor is off. This is just like an open switch. If the voltage grows past VTH, then the transistor is on and there's a path, right? Drain and source are connected. Okay. Any questions so far? Now you might start seeing why the labeling of the source and drain is simplifying our life, because otherwise this definition would be something like, if the difference in voltage between the gate terminal and the higher voltage terminal of the diffusion terminals is larger than VTH, right? That's, let's just first figure out which thing is at a lower voltage and then figure out what the delta is between the gate and that terminal, and that's the source. Okay, same thing for PFETs, right? Or basically complementary definition for PFETs. So if the difference between the source and gate terminals, the voltage difference between those terminals, which we call VSG, the voltage from the gate to the source, is larger than the threshold, then the PFET is on, otherwise it is off, right? So if there is a small voltage difference between these two terminals, then the transistor is off, otherwise it is on. So this is a little bit more detailed than the model, or than what we saw in the first slide, right? That a high voltage creates a conducting path here, and a low voltage creates a conducting path here. But you see that if you have a low voltage here and a high voltage here, right, then the voltage difference here is going to be pretty high. And so that is why you get a conducting path. Okay, so with this, we have everything we need to build gates. So let's do just that. Let's start by analyzing one gate. This is a pretty simple one. So there are two transistors here, right? We have V in, the input voltage to the gate. So there's one input terminal, one output terminal. The input is connected to the gate terminals of these two FETs. There's a PFET up top here and an MFET on the bottom part. The PFET is connected to VDD here, and the MFET is connected to ground over here, and then both are connected to the output terminal, right? V out. So the first thing that we need to do when analyzing the behavior of a CMOS circuit is to label the source and drain. So can you tell me which of these terminals are source and drain for both the PFET and the MFET? Yes? Uh-huh.
I assume ground is going to be the drain.
Ground is going to be the drain for which one?
For whichever one at the lower voltage.
Ah.
The PFET.
But remember, we said that for NFETs, the source is at the lower voltage.
So for
So it's just the opposite. The source is here for the MFET, and the source is here for the PFET. It's a bit confusing, but remember, they have opposite definitions. So we label the terminals this way, right? Source, drain, drain, source. Okay, now that we have the terminals labeled, and I mean it's pretty clear that this is going to be always at a higher voltage than anything than this terminal. It's going to be at a higher voltage than anything else in the circuit, right? That's VDD. Same deal for the source of the MFET. Now, let's assume that this threshold voltage is smaller than VDD over 2, right? And so what I want to do is we can go and draw the VTC, the voltage transfer characteristic, right? So remember, VTC, you put V in on the x-axis, and then you have V out, right? We have VDD. So if we have a very low voltage at an input, what's going to happen? Right? So you have V in, let's say, 0, ground. Which of these transistors is going to be conducting? Sorry? Which of these, so we have an MFET and a PFET, right? If I have a very low voltage, let's say V in equals 0 volts, right? V in is the ground. Which of these two transistors is going to be conducting, and which of these two transistors is going to be not conducting? Yes?
The top one will be conducting.
Exactly, right? Because we said that at a low voltage, right, VGS here is very high, or VSG is very high. So you have a very low voltage at the gate of the PFET. So this transistor's on. And then there is a low voltage here, right? So there's no voltage difference between these two terminals. So this MFET is off. And so what is V out? Basically VDD, right? Let's go to the other extreme, right? If I said V in equals VDD, what's going to happen? Which transistor will be on and which transistor will be off if I set a high input voltage?
The MFET will be on.
Right. So the MFET will be on and the PFET will be off. And so we have a low voltage at the output. And this behavior will be the case, will be true in these regions, right? VDD minus VTH. What happens in this middle region? Both transistors will be sort of on, right? So as you can imagine, nothing is binary in real life. So what happens here is the MFET will start turning on, the PFET will start turning off, and you'll get this transition in the VTC. Can you see why this is a valid VTC? What would I choose as VIH, VIL, VOH, VIL, VOL? So we get almost VDD and 0, right, at the output. So we could set VOL as almost 0 and VOH as almost VDD. And then VIL could be VTH and VIH could be VDD minus VTH. And this would give us these forbidden zones, right? And if I wanted to maximize my noise margins, what value of VTH should I pick? Do you want VTH very close to 0, or I don't know, large, somewhere in the middle? So remember, what is the noise margin? Can anybody tell me what the noise margin is? It's the amount of noise that you can tolerate from an output to a downstream input, right? So that's the smallest of the differences between your output and your input levels. To have high noise margins, you want these boxes, right, to be, or these two levels to be as far away as possible, right? You want the difference between VOL and VIL to be large, and the difference between VIH and VOH to be large. So what do we want? We want to set VTH close to VDD over 2, right? So that way, imagine that we had, some wonderful transistors that had just VDD over 2. Our VTC would look just like this, right? Where this is VDD over 2. It's actually pretty close to that. So these are very good switching devices. Okay, what does this implement? What function does this implement? Let's forget about voltages for a second and think about digital zeros and digital ones. If I have a digital 0 at the input, what output do I get? A 1. And if I have a 1 at the 0 at the input, I get a 0 at the output. So what device is this? An inverter. Yes. So this is how you build a CMOS inverter. Now CMOS is kind of a weird term. Let me just make a small aside on terminology. There's multiple names for field effect transistors because there are multiple types of FETs. And the most common type is what we call a MOSFET, which stands for metal oxide semiconductor field effect transistor. For that reason, we'll sometimes call these MFETs and PFETs as NMOS and PMOS. And this is kind of a dated terminology. Normally we use MFET and PFET. But because this was used in the past, what has stuck as a term that's commonly used is CMOS, which stands for complementary MOSFETs or complementary MOS. Okay, so we'll see what complementary means in a second. But before we do that, let's continue analyzing a slightly more complicated circuit. So here we have 2 transistors, 2 PFETs here, and 2 MFETs, right? And again, we have sort of a similar formula. The inputs are connected to the gate terminals, and then there are MFETs here in the low part of the circuit, PFETs in the upper part of the circuit, and then the output is sort of at the interface between these MFETs and PFETs. Okay, so let's without going all the way to voltages, if I have a low voltage that is a digital 0 at the input A and also a 0 at the input B, what's the output? Is it 0 or is it 1? Is it low or is it high? Which transistors are on? Yes?
The PFETs.
Precisely. So both PFETs are on, both MFETs are off, and so of course VDD is connected, C is connected to VDD, and so we have a high voltage at the output. How about 0, 1? So if we do 0, 1, this PFET is still on, this PFET, however, is off. And now this MFET is still off, but this MFET is on. But because these are connected in series, this is still not connected to ground. And we do have a path to VDD through A, right? So this is still 1. This circuit is symmetric, so of course 1, 0 is going to be 1. And then what happens when we have 1, 1? Both PFETs are off, and both MFETs are on. So now they're driving the C terminal to a low voltage, to a digital 0, right? What function is this? We've seen this already, right? Remember this truth table? What gate was this? An AND, yes, it's a 2-input NAND. CMOS NAND gate. We have this symbol, and of course, always remember the bubble. So let's generalize this and see where the term CMOS comes from. Basically, the C stands for complementary, and what this means is that you have the following structure. You have the inputs are connected to the gates of the transistors in your circuit, and then you have both a pull-up circuit and a pull-down circuit. The pull-down circuit is going to connect, under some combination of inputs, is going to connect the output to ground, and the pull-up circuit, under some combination of inputs, is going to connect the output to the power supply, to the supply voltage, to VDD. And the reason we call this complementary is because these pull-up and pull-down networks are never both on at the same time or off at the same time. When one is on, the other one is off. When one is off, the other one is on. They have complementary behavior. And why is that important? Well, let's see. If the pull-up is on and the pull-down is off, right, then we're driving the output to the power supply voltage, to a high voltage, to a digital 1. Conversely, if the pull-up is off and the pull-down is on, we are driving the output to a digital 0. What happens if the pull-up and the pull-down are on? Disaster, right? Fire, horrible things. The circuit will start burning, right? You just short the supply and ground. Don't do that. Okay, what happens if both are off? We just left the output floating, right? And so, who knows? There's going to be noise in there. It's going to drift to some value. We also don't want to leave both off. Although if you have to choose, then definitely don't do that. Okay. Still remember when I was building one of these gates with actual discrete transistors, and I connected them wrong, and then they started smoking. And it's funny because when transistors start smoking, they all begin smoking in the same pattern and at the same time, and so it's mesmerizing. So, yeah, it's really beautiful for 5 seconds, and then you have to grab the fire extinguisher. Okay, so that's the rule number 1 for CMOS is pull-up and pull-down networks are complementary. The second rule is that we use PFETs to implement the pull-up network, and we use MFETs to implement the pull-down network. We've seen this in the 2 gates that we've seen so far. Let's see what happens when we go and violate these 2 rules. Okay? So let's see some questionable gates. These are not CMOS gates, but let's see what could go wrong. If we have this innocent-looking gate, what combination of inputs could cause mayhem here? So you have 2 PFETs in parallel and 2 MFETs in parallel. Yes?
A is 0, B is 1.
Precisely. So if A is 0 and B is 1, you have a conducting path from VDD to ground, and you don't want to do that. Right? So these are not complementary networks. Not complementary pull-ups and complementary pull-downs. The second case, so the first rule, again, complementary pull-ups and pull-downs. This second gate over here is a little bit more subtle, and this is why you have to watch out for where is the source and where is the drain. So let's spend a minute analyzing this gate. If I just give you this gate and I give you the simplest possible rules, right? That high voltage here makes this MFET conduct, and a low voltage makes this PFET conduct. What function would you expect this gate to implement, this circuit to implement. So, if I give you a high voltage, then this is going to be on, and so we would expect a high value at the output, and then a low voltage would cause this to be on, and so we'd get a low voltage at the output, right? So a buffer, right? Except that's not how it works. Okay, if we go and label the terminals again, where are the source and drain for these transistors? Remember, for an MFET, the source is the terminal at the lower voltage, right? So is it this? It's this. The source is this terminal over here, and likewise for the PFET, the source is this terminal over here. That's the higher voltage terminal. Now, note how this is different from whenever we have MFETs in the pull down and PFETs in the pull up, right? Here the source is at VDD, and here the source is at ground. So what's going to happen here is that this PFET is not going to pull down the output below the threshold voltage. It's not going to drive it down to 0. Why? Well, suppose that you start with a high value, a high voltage here, right? And then you set V into 0. So for a while, this will be on because there will be a high voltage between these two terminals. But then the voltage at this terminal will go down. And when VGS or VSG becomes VTH, this transistor will close. And also, this transistor will be closed the whole time, right? Conclusion, you just left it floating. So if you draw the VTC for this, what you'll see is that instead of pulling the output voltage all the way down to 0 and all the way up to 1, as you reach both VTH or VDD minus VTH, these things will stop pulling up or down. And so you end up with this. Is this a valid digital device? I see many of you saying no. Why? You can't draw a rectangle here that, a set of forbidden zones that gives you any valid behavior, right? There's no gain in the middle, in other terms. Okay, so remember, rule number 2, PFETs in pull-up, MFETs in pull-down. Once you remember that, you can actually think of PFETs and MFETs just as normal switches and even forget about VTH. But remember, the reason why we have this rule is that if you build gates this way, they won't work. Okay, so now let's say that we want to derive some particular functions, right, that are not just AND or some other simple gates. We want to derive some more complicated functions and implement them using CMOS gates. So there are some very simple rules that you can follow to do that very systematically, right? And that's looking at different connections of different transistors, both NMOS or NFET and PFET. So a single transistor, a single MFET, and a single PFET are complementary, right? Because this conducts when A is high, this conducts when A is low. We've already seen this with the inverter. When you have two MFETs in series, the complementary network is two PFETs in parallel. And we've seen this with an AND gate. Why? Because this conducts only when A is high and B is high, and this conducts only when A is low or B is low, and remember, by de Morgan's law, that is when not A and B. So these two networks are complementary. And the reverse is also true, right? Two MFETs in parallel are complementary with two PFETs in series. And because this holds for these basic networks, this actually holds for much more complicated networks. You can go swap parallel and series and get a complementary network. And so, if you want to build an arbitrary gate, or a gate that computes a certain function, then let's say that I give you, this Boolean formula here. F, we want F to be not A or not B and not C. one way to do this is first derive the pull-up network, essentially derive the connection of pFETs in series and in parallel that is going to drive the output to 1 whenever we want. So this, you can see that there's a very clear mapping between the formula and the circuit schematic, right? So this is 1, the output is 1 when not A, right, because this transistor will be on, or when not B and not C, because then both of these transistors will be on and will overall be conducting, right? Then we can just derive the complementary network by replacing all the series subnetworks with parallel subnetworks and all the parallel subnetworks with series subnetworks. So what is this? Well, this is this. There are two things in parallel, right? So let's put them in series. So that will be A with whatever subnetwork here we have. But now this is two things in series, so we have to change them to be in parallel. And that is the complementary NFET network. And then the only thing we have to do is to just connect them both together. Done. You can now implement gates, CMOS gates, for anything you want, any function you want, right? Well, not quite, right? Can you implement an arbitrary function using a single CMOS gate? So it turns out you can't. And we've already kind of seen this with the buffer. If you try to implement a buffer, it just doesn't amplify. But there's a very simple rule, or a very simple restriction that CMOS gates have to obey. And that is that CMOS gates must be inverting. And what I mean by inverting is that rising inputs will always lead to falling outputs, and vice versa. That is, falling inputs, that is, if we go from a 1 to a 0, will lead to rising outputs. You cannot have a 0 to a 1 in an input cause the output to go from 0 to 1. Let's see why. If you have a rising input, right, if one of your inputs goes from 0 to 1 and the other inputs stay the same, what is going to happen? Well, the MFETs are going to go, some MFETs are going to go from off to on. So now the pull down might go from not connecting the output to ground to doing that. And then the pFETs, at least one of the pFETs will go off. So it might disconnect the output. If the pull-up network was conducting, it might go from conducting to not conducting. Or maybe things stay the same, right? So the corollary here is that the output either stays the same or falls. And likewise, you can repeat the same process, right? If an input falls, then MFETs are going to turn off, pFETs are going to turn on, and your input can only go up. Your output can only go up. And so the corollary here is that we cannot build non-inverting logic as a single CMOS gate. How do you figure out whether your gate is inverting or not? Well, you just take a look at the truth table. Why is AND not inverting? Can you tell me about any rising input that would cause the output to go from 0 to 1? So if we're in a situation like here, where we have A set to 1 and B set to 0, and then we change B from 0 to 1, then what will happen to the output? It will go to 1. So a rising input causes a rising output. This, right, transition from 0,1 to 1,1, this is also a rising input that causes a rising output. So you cannot implement AND with a single CMOS gate. You have to use an AND gate followed by an inverter. Which is why when you go to the standard library, you'll see that there a NAND gate is pretty much an AND gate followed by an inverter. And that's why when we told you before that the synthesis tool will use inverting logic, this is why, right? Because that's a single CMOS gate. Okay, so in the remaining 10 minutes, we're going to spend some time looking at the physical characteristics of transistors and why that has some implications on the delay and area of these gates. Now, this is not going to be in the quiz. This is too close to physics. And so this is just for your own intellectual curiosity, and so that when you use the synthesis tools, you have some idea of what is going on. So here's how a transistor looks in a 3D schematic. So you actually have a slab of silicon over here, and then you have the two diffusion terminals, source and drain, and a gate terminal. The gate terminal is right here in the middle. Now, this is kind of hard to see, so it's easier to see some 2D cut of the of this. So if we do a 2D projection of this structure, you'll see that essentially, we can see why these are called MOSFETs, because this gate terminal is implemented using a bunch of metal, and then in the middle, on the other side, we have this semiconductor slab, right? This is just a chunk of silicon that's doped with different other materials. And then we have some thin layer of oxide here that acts as a dielectric. That is, it does not conduct. So what happens is, this silicon slab is doped with different materials. So we have an N-type semiconductor here because we add dopants like arsenic that essentially add electrons. And then we have a P dopant here, something like boron, that makes this part of the silicon add holes. And by default, if you have no voltage here, if everything is at 0 volts, then what happens is that there's a deficiency of electrons here, so there's an abundance of holes, which are also electricity carriers. And there's an abundance of electrons here, so they repel each other. So in the middle, you have this non-conducting band that we call the depletion region. Now, as you increase the voltage at the gate, what happens is that this gate acts as a parallel plate capacitor. So you have holes in here, and this attracts electrons over on this semiconductor side. And this is a dielectric, so it doesn't conduct, right? So again, you put charge in here, right, and this attracts electrons. And at some point, a channel forms between the N-doped terminals. And lo and behold, that low resistance channel is what causes, when we looked at the switching model, that's when we say the transistor is on. Now, the shape of this channel is subject to all sorts of differences in the voltage between terminals, but we're going to ignore all of that because all we need to know is at an electrical level, a transistor is going to be essentially modeled as a capacitance, because the gate terminal, remember, has this dielectric, and so it's just like a parallel plate capacitor, and then a resistance between the source and the drain. And this resistance varies depending on the voltage at the gate, right? If the voltage between the gate and the source, or the source and the gate, is below the threshold voltage, then this will be R off, a very high resistance, almost like not being connected. And then if the voltage at the gate is high for this MFET, then this will be the resistance when the FET is on, a low value, right? So ideally, you want to build transistors that have very low on resistance and very high off resistance, right? Unfortunately, life doesn't let you do that. So, generally, the lower you want to make the on resistance, the lower the off resistance is going to be, and so some current is going to leak even when the transistor is off. Same thing for PFETs. This model is also horribly inaccurate, but it is actually accurate enough so that you can understand how sizing the transistors affects delay. So let's look at that. So suppose that I give you this circuit, right? This is a pair of inverters, and for t less than 0, I just have a constant, very low voltage at Vin. And then I apply a step function so that at t equals 0, Vin goes from 0 to VDD. right? So this is an inverter, so V out, when V in is 0, is going to be high, right? But when I apply this step function here, what do we expect to happen? Well, after some time, this will go down, right? But what's the shape of this transition? Well, let's go back to 802, right? This is how the circuit actually looks like when you look at the transistors. And what you end up with after t equals 0 is with an RC circuit, where this resistance is the on resistance of this transistor, right? So this transistor is going to be on, this transistor is going to be off, right? Because this output is going from 1 to 0, so now this is connected to ground. And then this output terminal is also connected to the gate terminals of both transistors over here, right? And remember, these are just capacitors. So the capacitance is the sum of the capacitances or the sum of the gate capacitances of both transistors. And if I give you this RC circuit and the boundary condition that V out 0 is some particular value over here, can anybody tell me what will happen? How would you go around solving this? You have a first order differential equation. No. This is why this is not on the quiz. So you have a first order differential equation, right? So V is IR, right? And it's also I is the current through a capacitor is minus C dV dt, right? The derivative of the voltage over time. And so you get, if you solve that first order differential equation, you get that V out of t, for t larger than 0, is V out of 0 multiplied by this falling exponential. And what I want to emphasize here is that there's an RC factor here, right? This exponential falls with t over, we generally call this tau, because this is a time constant, that is the product of this resistance and this capacitance, right? The larger this is, right, the smallest or the slower this output is going to fall. So if we go back to our definition of propagation delay, right, remember we now know that these are exponentials. What we want, right, is to minimize propagation delay, which is, remember, the time from reaching a valid input to reaching a valid digital output. And it's the maximum of these two thresholds. So what do we want? We want to minimize R's and minimize C's. And unfortunately, you cannot build arbitrarily small R's and C's. However, you can make some trade-offs as to how you size your transistors. So there are two dimensions here. The first one is the length between, or the distance between the source and drain terminals. We call this L, and this is the channel length. And then we have the width, right? How wide is this transistor? You could put a lot of material, right, and have a lot of a very wide transistor. You could do, a very narrow one. So the one thing I want you to remember is, how do the gate, how the capacitance of the gate and the resistance of the channel change as you change the length and the width of this transistor. So let's start with the capacitance. What is the capacitance of a parallel plate capacitor? Does it grow with the length? Does it grow with the area? Yes, right? It's proportional to the area between the parallel plates. So it's proportional to the product of the length and the width. How about the resistance? Right? If I just have a slab of material, right, the more wide it is, if current is flowing, right, between these 2 points, the wider it is, the lower it is going to be. And I want this length to be ideally very short, because that's also, the longer the distance is between these 2 points, the more resistance am I going to have, right? So the resistance of this rectangular resistor right, grows with L over W, which means that you want to minimize L. You want small c, small l. You want to choose L as small as possible. And that is why the smallest feature size that you find in chips today is the width of this channel. And billions upon billions of dollars are invested every year in trying to push this width down, right? And then, this length, right, this channel length down. And then this width depends. If you make it larger, your transistor is going to be, well, first it's going to take more area, but it's also going to be better at driving outputs, right? So if you connect something to a very wide transistor, it's going to drive it much faster. On the other hand, its capacitance is also going to be larger, so it itself is going to be harder to drive. So now in lab 4, what you'll see is that you'll have a new library that uses gates of different sizes. And what happens is the synthesis tools will combine transistors of different sizes, or gates with transistors of different sizes, to use the best possible combination to minimize delay, right? And so in the end, we don't size transistors individually, but the synthesis tools essentially use these collections of gates that have some very carefully designed layouts, right? So when we say the area of a NAND gate is like this is because there's a physical layout of the NAND gate that has all these components. And when you use the synthesis tool, you're going to be trading off area and delay using all these combinations of gates. Okay, that's all for today. Thank you.